So for this lecture, we're going to introduce the first version of the fundamental theorem of calculus. So this is the derivative of the integral formation of the fundamental theorem of calculus. You can imagine by the name being fundamental theorem of calculus, this is a pretty important theorem. So let's start with a function. So we're going to let t be our variable here, and we're going to consider y equals f of t on some closed interval from a to b. Now notice if I pick any x value in the interval from a to b, I can consider the definite integral from a to x of f of t dt. And this is going to output a number. For instance, if f is always positive on this interval, this would be the area between between t equals a and t equals x under the function f of t. So since this is a function, since this outputs a number for each x, we can consider this a function. So for each input x, we output a number. That's exactly what we want to do for a function. So we'll define this to be big F of x, to be the integral from a to x of f of t dt. Just keep in mind the integrals we've been doing up to this point, we had x as our variable. Here we're using t under the integral, and x is the variable for what we're going to be outputting. So for instance, if we let f of x be x squared and a be 0, our function f of x would be 0 to the x of t squared dt. You could also write this as f of t is equal to t squared. It doesn't really matter the variable. It just matters in here. You can't have the variables in the limit and the variables inside the integral be the same thing. So notice the x is what's going with our function for the outputs. So if we were to look at what these look like, so if I look at f of 2, that's the integral from 0 to 2 of t squared dt. So it'd be exactly this area here in the area of the shaded region here. And if we look at f of 3, it would just go from 0 to 3 now. So we would get this full shaded region here. So for us, we could see, for instance, this function here is an increasing function because as x gets bigger, I have more area coming into this. So the function big F of x is increasing. So it's natural to ask then, if I change x, how does f of x change? And we know when we're looking at how does f of x change, as x changes, what we're really looking for there is the derivative. So what I might like to find out is, what is the derivative of this capital F of x? So this is our first fundamental theorem of calculus. So if we let y equal f of t be continuous on the interval from a to b, then capital F of x, which we define to be this integral from a to x of f of t dt, is a continuous function on ab, and it's differentiable on the open interval ab. But the important part here that we get out of this is a nice formula that the derivative of this is just whatever the function inside the integral is. So we just get little f of x back when we take this derivative. So the reason we refer to this as the derivative of the integral formula is we're saying if I take this integral here, and I take the derivative of the integral, what do we get back? Well, essentially, it just gets rid of the integral, and we just get the inside function little f of x back. So we can think of this as the derivative undoes the integral and just gives us our function back. So it's important to remember this theorem. We're going to go through and sketch a proof of it now, mainly because it combines a lot of the stuff we've done during this semester into this proof, but we're also doing this in the flipped class video, so we're not spending in-class time on this proof. You're not going to be tested on the proof. I wouldn't expect you to be able to reproduce it, but it is nice to be able to make sure we understand where all of the steps are and where the steps are coming from. So we know whenever we're going to calculate a derivative, and it's not one that we already have a shortcut for, we have to use the limit definition of the derivative. So we're going to need to look at this limit as h goes to 0 of capital F of x plus h minus f of x over h. So that's what we've been working with right at the beginning of this semester for finding derivatives. So let's start by looking at just the numerator here. So forget about the limit, forget about the h. Let's just look at this top part first. So just the f of x plus h minus f of x. And let's see if we can figure out what this is actually measuring. So notice if I have f of x plus h, remember that's the integral from a to x plus h. So that's going to be the area of this entire shaded region here. That's f of x plus h. Now, what am I looking at? I'm looking at that area, and then I want to subtract f of x from that area. So what does f of x look like? Well, f of x is the integral from a to x, so it's this shaded area. So if I want this shaded area here, and I want, notice the f of x is the area from this line between a and this line. So if I subtract those two, all I'm going to be left with is this part here, which we see is just this. That's the difference. So this shaded region is f of x plus h minus f of x. But we can also recognize that as that's the integral from x to x plus h of f of t dt. So it's just this little area here. So that's what the quotient is, or the numerator of our quotient is measuring. It's just the integral from x to x plus h of f of t dt. And now that we have that, we can actually work with that. So notice if I divide both, so I have this formula here, divide both sides by h to get back to the quotient we're looking at. And so this is the thing on the left here. I want the limit as h goes to 0 of this will give me my derivative, which means the derivative is also equal to the limit as h goes to 0 of the right-hand side here. And this right-hand side is exactly what we're going to calculate and take the limit of. Now we're going to bring in the extreme value theorem from back when we were doing optimization in functions of one variable. So since I know my f of t, little f of t, is continuous on AB, it's certainly continuous on any subinterval of AB. So it's continuous on the subinterval from x to x plus h. So the extreme value theorem, if you recall, says that we have an absolute maximum and an absolute minimum on that interval. So another way of saying that is there's a u and a v in the interval, so that f of u is the absolute minimum and f of v is the absolute maximum. So every value f of t has to fall between f of u and f of v. So we can use that then to say, well, what is this integral on the left-hand side here? Well, it's the area under the blue curve here from x to x plus h. And notice, what is f of v? Well, this is my function f of v, is just the red line. And so if I look at the rectangle here, the area of that rectangle is f of v times the width, which is h. So f of v times h is the area of the pink rectangle, which is certainly bigger than whatever the area under the blue curve here is. So I have that this integral is less than or equal to f of v times h. And similarly, if we look at f of u, this is the smallest value on the interval, so in this case it occurs at the left edge point, and f of u times h is the area of the pink here, and this integral is the area of the blue, or everything under the blue curve here. So it's this little extra blue plus all of the pink here. So it's certainly bigger than f of u times h. So that means we have this nice bound that f of u times h is less than or equal to the integral, which is less than or equal to f of v times h. So divide everything in this string of inequalities by h, and I get f of u is less than or equal to 1 over h times this integral is less than or equal to f of v. And now remember, this integral on the inside here between the two edge points here, if I take the limit as h goes to 0 of this, that gives me exactly the derivative I'm looking at. So what we want to do is take the limit as h goes to 0 of this whole thing. Now remember, u and v lie in the interval from x to x plus h. So if I let h go to 0, this right-hand side, x plus h, is going towards x. So u and v are pinned between x and something getting closer and closer to x. So as h goes to 0, u and v have to both go towards x. So what that means is f of x is the limit as h goes to 0 of f of u, because u is getting closer and closer to x. I know that f of u is less than or equal to this, so the limit is less than or equal to this. And we know that this thing is less than or equal to f of v, and that's f of x. So if f of x is less than or equal to this limit, which is less than or equal to f of x, that limit has to be equal to f of x. So this limit in the middle is the derivative, so the derivative is little f of x, just like we claimed. And so that gives a sketch of the proof here for this version of the fundamental theorem of calculus. And so it's pretty easy to use this version of the fundamental theorem of calculus. We'll do one simple example of it here, and then we'll do some more complicated examples in the regular class lecture, because we can have things like chain rule and things like that that come in that make it a little bit more complicated. But for now, let's look at a fairly simple example. So let's look at to find the function f of x to go from 1 to x of 1 over t cubed plus 1 dt. And suppose we want to find the derivative of this. Well, in this case, the function I'm looking at, little f of t, is 1 over t cubed plus 1. So the fundamental theorem of calculus says if I take the derivative of this, I just plug in x for this, and that's the derivative. So f prime of x is just 1 over x cubed plus 1.